This is the Scalar Network Analyzer that I built. We have here is an Arduino Nano. This costs $3 or $4 from China these days. This is an AD9850 DDS module. I think these can be had for $8 or $10 from China. This is a very small DDS amplifier. It's 2 transistors and a handful of R's and C's. I built it as an SMT module here, but it doesn't really need to be made that small. Under this can, there's an AD8307 power measurement chip. The circuit's on the web page, and you need this for shielding because it's a very sensitive part, and if you want to get good results, it needs to be well shielded. That's the bottom of the board. Not a whole lot of wiring there. I used SMAs. This one is not actually connected at the moment. I may use that for a square wave output from the DDS in the future. So what I've got hooked up is I have the DDS output, which is nominally about 1 dBm. Through the cable, I have a 10 dB attenuator in here. And we're going to be testing this little 30-meter low-pass filter. So if I launch the Python application, you can see now it's talking to the network analyzer module and it's scanning. So various things I can do here. I can increase the number of samples up to 1,000 samples per sweep, and of course it gets slower when I do that, but it gives you a lot more data, and it tends to smooth out the data as you increase the samples. But for demo purposes, I'm going to go back to a relatively low number of samples, 100. So I know my filter is about is a 30 meter, so it should roll off about 10 megahertz. So let's change the sweep from 5 megahertz to 30 megahertz, and we can see what it does here. So I'm going to calibrate the network analyzer. So what I do here is I press the ref calibrate button. You see my signal here, the loss through the attenuator is about 10 dB. I have my output of my DDS amp is set to nominally about 0 dBm, so it would be about 0 minus 10, but minus 10 dBm, or minus 10 dB rather. So if I calibrate, it'll do one sweep, it records those readings, and now if I turn the reference on, it jumps up to 0 dB. So that's my reference level, and I've calibrated out all the nonlinearities in the DDS and little frequency bumps, etc. So now what I'm going to do is put the filter in line. So there we go, there's the frequency response of the filter. If I left click in the box here, I can set a marker, and you can see there's the frequency of the marker and the level. So we know up here is about 0, so let's minus 4, so if we minus 2, so there's the 3 dB frequency is about 9.1 megahertz. So it's rolling off a bit quicker than would be ideal. And if we look down here, if I right click, I can mark one of these points, and that shows me that I'm down now about 60 dB or so at 25 megahertz. So that filter rolls off pretty well. So the corner frequency could perhaps be a little further out here, but it's not bad for a 30 meter low pass filter. So some of the other things I can do here is I can change my reference level. So if I want to go up 10 dB or down 10 dB, whatever, I can also change the number of divisions. So I can go to 20 dB per step here. if I click on auto scale, it will automatically adjust the y-axis here so I get a nice view of my sweep. And I can store the trace, and then I can compare it to something else. So it's just sweeping the filter, so there's really not much to compare it to. But if I disconnect the filter, so now you have something to compare it to. So that's the Scalar Network Analyzer project. If you shop carefully and you can scrounge yourself a free sample of the 808307, you can build this thing for probably less than $20 or so. I also made a companion return loss bridge, and there's details of where to find this design on my webpage. And this is very useful for testing antennas and other devices as well. So it's quite a handy gadget, and you should add one to your suite of test tools in your ham shack.